All right, we will continue our discussion on the flash reliability. And this is what we discussed in the last lecture. So we have this 1/kt plot, this Arrhenius plot, to describe the retention of the non-volatile memory in general. Of course, here we apply that to the NAND flash. So basically, we plot the retention time or the time to retention failure in the log scale as the y-axis. And then on the x-axis, we plot this 1/kt. Kt is the thermal energy in the unit of electron volts. And then if you do that, this will be a straight line because the retention time follows this formula. The retention time equals to some coefficient, T0, and exponential, and then EA/kt. EA is activation energy. So from this plot, the slope of this line will give you the activation energy, EA. So here then you measure the device at higher temperature, for example 200C or 300C, and then you extrapolate the behavior at lower temperature to predict the lifetime of the data retention. So in this particular case, you see that if you extrapolate to like 10 years time frame, which is a typical spec for the non-volatile memory, so this is about 3 times 10 to the power 8 seconds. So if you do that, then the temperature here is about 114 degrees C. That means you can sustain the data for like 10 years at this temperature for this particular device. And here we also show different curves corresponding to different number of cycles. So typically for the fresh sample, for example, you only cycle it for like 10 times, then you may have higher data retention here. And if you cycle the device more than like 10 to the power 4 cycles, and after that, if you do the post-cycling retention, there will be a degradation. So you see that the retention time will be lower than the fresh sample. So basically here it says there is a trade-off between the endurance and the data retention. So this can be summarized in this slide as a trade-off between the endurance and the retention. So you know endurance, how many cycles you can write the data into the memory. And the retention, how long you can maintain the data. So there is a trade-off. Ideally, you want, for example, if your spec is for the endurance, you want 10K cycles, I mean 10 to the power 4 cycles, and you want the data to maintain at least 10 years. So this is the typical spec for the flash. But however, you have to trade off between the data retention and the endurance. That means if the device is in the initial state of the cycling, for example, you only cycle it 10% of the end life cycle time. So for example, you only cycle it for like 100 cycles or 10 cycles, 100 cycles, then you may maintain the data for 10 years. But if the device has been cycled many, many times, approaching the end of the lifetime, then the data retention may reduce to like 1 year. This is because after so many cycles, as we discussed before, you create so many damages to the ternal oxide. So there may be defects generated in the ternal oxide. Therefore, the electrons will be easier to jump out from the floating gate through those defects in the ternal oxide. So there's a trade-off between the endurance and data retention. So any questions? Not, then we're going to continue our discussions on the program disturb. So this is what we have already briefly discussed before. So in the NAND flash programming, we have the selected column and unselected column. So for the selected column, for example, here the blue cell is a cell that is going to be programmed, and we apply like a large voltage. Sorry, I think there is a wrong label here. So I should say, oh yes, this is correct. So this is the cell to be programmed. And then we have two other cells that are under like a disturb mode. So for the same page, the other cell, which is under the unselected bit line, will go through this self-inhibition as we discussed before. So we need to boost the channel potential to prevent this cell to be programmed. And we have the channel inhibition and the self-boost scheme as we discussed before. So the idea is that we have to increase the channel potential. Therefore, the active, or let's say effective voltage drop across the gate stack is reduced. So this cell will not be programmed. However, still you may have like 10 volts across that. So there is still small probability for electrons to turn into the floating gate. And for the other cell here on the same column, we have this V pass W voltage applied on the other unselected word lines. Therefore, here we may still have like 10 volts across this gate stack. So still the other cells along the same column will be under this disturb. So here, for both cases, the VTH threshold voltage for those cells under disturb may increase. So here we see the distribution of the VT of a multi-level cell. So here you see that the tail of the distribution tend to increase because here you may have more electrons inject into the floating gate due to the disturb voltage across the gate stack. So here there is a criterion for this V pass W. So this V pass W voltage is critical. So here you see that there is a narrow margin for the V pass W. If the V pass W is too large, you may imagine what will happen. If the V pass W, this voltage, if it's too large. So if this voltage is too large, then you see all of those cells along the same column will, of course, this is a string select. We don't have the floating gate here, but for the other cells, all of those cells may suffer from this V pass W if it's too large. For example, if the V pass W, let's look at the blue cell here. Then if the V pass W further increases for like 14, 16 volts, then the V pass this cell threshold voltage may increase, right? So this V pass W is getting close to the V programming. Therefore, this blue cell threshold voltage may increase as we show here. But if the V pass W is too small here, of course, the blue cell will be safe, right? So this is like only like 8 volts, 10 volts. It will not program. However, if the V pass W is too small, then this cell, this red cell on the same word line will have a trouble. Because if the V pass W is small, as we discussed before, so this inhibition voltage cannot be passed through here. Or the self-boost efficiency will be low. Therefore, if the V pass W is too small, then this transistor's channel potential here will be low. If the channel potential will be low, then the voltage across this cell's gate stack will be high. Therefore, this red cell will shift VTH to higher values, as we show here if the V pass W is too small. So you have the limitation from those two kinds of cells to determine the V pass W window or margin here. So it's only like in this particular case, it's only in the range of like 11 volts to 12 volts. So this V pass W has a narrow range in the middle somewhere in the middle. If the wave programming is like 20 volts, roughly like half of that, around 10 volts, 11 volts, will be the range for the wave pass W. The wave pass W cannot be too low, cannot be too high, because you have to balance those two kinds of cells. What are those two kinds of cells? The first kind is along the same column. The second kind is along the same word line. So those two will have conflict. So any questions here? And similarly, we may have the rate disturb. So here in the rate bias scheme, as we discussed, we have to apply this wave pass. This is the wave pass rate to turn on all the unselected word lines. And then for the selected cell, in this case, we apply 0 volts. So for the unselected cells, you will have like 6 volts on that. It's not that large, but if you keep doing so, still there's more probability for electrons to turn through. So I would say those are electrons. So here, if you keep doing rate on the other word lengths, the unselected word lengths may suffer from the rate disturb. But I would say the rate disturb is less a concern than the program disturb, because program disturb you may have like 10 volt or 12 volt on the unselected cells, but for the rate you may have at most like 6 volts. So then this is not a big concern as compared to the program disturb. But the effect will be similar because you apply positive voltage on the unselected cell, so therefore the threshold voltage may increase a little bit. And as a result, the threshold voltage may increase, especially for the erased state. Because in the erased state, your wave pass voltage is here. The wave pass voltage is higher than any threshold voltage of all the multi-level cells. So for the erased state, which will have elective VTH, so here effectively you have a largest voltage across the gate stack. Therefore, the effect mostly will affect the erased state. So the erased state may have this tail due to the continuous rate disturb. And also the rate disturb may depend on the cycling number. So basically after many cycles, you create more of those negative effects. Therefore, the rate disturb will be more prominent after the program erase cycling. All right, so let's have a summary of the reliability issues. So basically, you can summarize those reliability effects as a VTH distribution shift. So here we show example of MLC, 4 levels of the VTH distribution. So here, from this plot, you can look at the impact of each of the mechanism, what it may have done to the distribution. For example, if it's rate disturb, as we just described, mostly it will affect the erased state, and the erased state, the tail, will increase the VTH. And this is affected by the stress-induced leakage current, SILC, and also the detrapping. And the program disturb, so this is more prominent than the rate disturb because the voltage is higher across the gate stack. Therefore, here not only the erased state will have this tail, but also other states may have a little bit increase of the tail speeds towards higher VTH, because in the program disturb you may have 10 volts across that, and the rate disturb you may only have like 6 volts. And the endurance, as we discussed before, mostly is affected by the trapping, electron trapping in the turtle oxide, and this will effectively increase not only the tail, but also the mean value of the erased state VTH. So you will see a shift of this distribution, because you cannot get rid of all the electrons out from the turtle oxide. Effectively, the VTH mean value will increase. And data retention. So there are two mechanisms. One is the SILC. This will depend on the voltage polarity. So for the erased state, you will see a tail due to the SILC. And also for the program state, you will see a tail depending on the SILC. And then the other mechanism is detrapping. So electrons may spontaneously get out from the floating gate due to the detrapping. And then this will reduce the VTH. So you see that all the distributions shift towards the left a little bit due to the detrapping. And there's one last mechanism. Sometimes you may see this like tail for all the program states. This is caused by this erratic overprogramming. And this is because somehow if there is like hole trapping in the turtle oxide, then this hole trapping, this hole will basically burn down the like a positive voltage, right? Positive charge is like positive voltage. This will burn down the band, create this kind of valley in the band diagram. Therefore, effectively, the electrons will see thinner barrier to tunnel through. So electrons will be easier to tunnel through. That means the electrons will be easier get into the floating gate. So somehow if you use the same programming condition, you get more electrons into the floating gate. Therefore, you may have this over-programming if somehow you have the hole trapping in the turtle oxide. This may not happen very often, but in some cells, you may see this over-programming. This will impact all the tails towards higher threshold voltage. So here, this is a quick summary of the reliabilities in the NAND flash. So any questions? If no, then we will continue on the scaling challenges for the two-dimensional NAND flash before we talk about the 3D. So here, this is the scaling trend, including both logic transistor, like SRAM we discussed before, and then DRAM, and then NAND flash. So this is like the feature half pitch F, equivalent F, shrinking over the years. So basically, we discussed before, the DRAM actually outpaces the logic in terms of scaling. And the NAND flash outpaces the DRAM and logic in terms of scaling. So the NAND flash, the two-dimensional NAND flash, used to be the driver for the lithography technology to push for the smallest feature size on chip. Because the NAND flash, like the word line, the pitch between word lines, the smallest feature you can fabricate on the chip is actually smaller than the logic design rule in the SRAM and so on. So the NAND flash is highest density in terms of the feature size. So the NAND flash really push for the scaling of the feature size. Till here around like 2013-14, it approached to like this 15 nanometer or 14 nanometer, around let's say 15 nanometer dimension. This is a real number, the technology load as we discussed in the NAND flash and DRAM, really means the feature dimension, physical feature dimensions on chip. It's unlike logic. Logic, there's no correlation between the technology load and the physical dimensions, like 5 nanometer, 3 nanometer, there's no 5 nanometer, 3 nanometer on any structure of the chip in logic. But for NAND, if it's 15 nanometer NAND flash, that means really the smallest feature size is 15 nanometer. So this is end of the 2D NAND scaling around 2013-14. And after that, then the industry switched to the 3D NAND, because this one really cannot scale due to the challenges we will discuss in the next few slides. So for the 3D NAND flash, we use the third dimension to stack more cells vertically, and in that case, the feature size actually relaxed back to 60 nanometer for the half pitch, or even 100 nanometer for the half pitch. So the 3D NAND flash actually has larger dimensions in terms of lateral dimensions, but it will stack more cells vertically. So the 3D NAND flash is no longer limited by the lithography. It is more limited by the etching, as we discussed later. So this is the general trend. And here, this is a quick summary of the NAND flash scaling trend over the past 30 years. So you see the structure change from the very old days, the low cost, thermal, this is low temperature, the thermal isolation between the active region, and then you change it to the STI, shallow trench junction, for the isolation, and then this is keep going, and then we introduce the multi-level cell, and then triple cell, TLC, triple level cell. So you keep decreasing the effective cell size, and then increase the chip capacity to 128 gigabit per chip, or even 256 gigabit per chip. And then this corresponds to the technology load for the NAND flash for this 1X load, 1Y load. So as we discussed earlier, the companies may not disclose the exact dimensions, so they use 1X to refer to the first generation below 20 nanometer. It's 1X, about maybe 18 or 19 nanometer, and then 1Y, and maybe 1Z. And after that, then we switch to the 3D NAND flash. So then we have the 24 layers, and 64 layers, 128 layers, and today's 176 layers. So this is a general trend. And let's discuss why it's so difficult to scale the two-dimensional NAND flash towards 10 nanometer. So we never reached the 10 nanometer. So we stopped at about 14 or 15 nanometer, and we switched to 3D. So there are some limitations prevent us scaling to 10 nanometer node. So here are a summary of the scaling challenges for the two-dimensional NAND flash. So here I will not read one by one, but basically there are many challenges related to the design. So here, for example, we can look at a few. The first one is so-called cell-to-cell interference. So this is between the floating gate, you have the coupling, active coupling. So the cell-to-cell interference will impact the VTH distribution, as we discussed later. And then we will have this number 6. We will discuss this number of electrons is so limited in the floating gates. It will cause this few electron problem. So let's look at those two particular problems in more details. The first one is the cell-to-cell interference. Due to the smaller pitch as we scale, so the word lengths become closer to each other, the distance between the word lengths or between the bit lengths will increase because the distance between those metal lamps decrease. So the cells may be capacitively coupled to each other. So for example here, if this is your selected cell, due to those parasitic capacitance, this cell may capacitively coupled to neighboring cells. So there will be the bit-line to bit-line, word-line to word-line coupling. Therefore, when you select this cell to program, you may affect the VTH state of the neighboring cells due to the capacitive coupling. This is the first problem. And the second problem is the few electron problem. So the number of stored electrons in the floating gate is so limited. So here, this plot shows the number of electrons stored in the floating gate as a function of the technology load. As you see here below, like 30 nanometer load, the number of electrons you store in the floating gate only like a dozen, maybe 50 electrons. So 50 electrons in the floating gate. If somehow you lose 1 or 2 electrons, then your VTH may shift significantly if you lose just 1 electron from the floating gate. Previously, if you have 1,000 electrons in the floating gate, you lose 1, your VTH shift like 0.1%, doesn't matter. But here, if you lose 1 electron, then your VTH may shift quite significantly. Therefore, your margin will be much reduced, especially for the multi-level cell. So let's look at the cell-to-cell coupling. So as the distance between the cells get closer, the coupling here will be increased. So here this is technology load, and then we see the coupling increases with the scaling. So you may have the bit-line to bit-line coupling, word-line to word-line coupling, and also those diagonal cells, you may have the coupling. Of course, diagonal cells will have less coupling because the distance is further out. But for the word-line to word-line and bit-line to bit-line, you will have the strong coupling. So what does this mean, coupling? This coupling means that you will have the VTH shift. So think about the programming order of the flash. We discussed before, so we have this page-by-page programming. So you first program the first page, the word-line 1, and then you move on to the word-line 2. So after you program the word-line 1, the electrons already stored in this floating gate, and now you program the word-line 2 here. So you apply large voltage here, like the UV programming. But due to the strong coupling here, if the capacitance is the distance so close, the capacitance is so large, so this voltage will be capacitively coupled to here. That means part of this voltage will drop on the first cell. This is already been programmed. You will not go back here, as we discussed before, the red pointer, right? You will move one by one. So after you go to the word-line 2, you will not go back to word-line 1. However, here when you program word-line 2, you will further have some voltage drop on the word-line 1. That means you are going to have more electrons inject into the word-line 1. So the VTH of the word-line 1 may further increase. This will be a problem, especially when you consider the multi-level cell. So if you look at the distribution of the VTH states, let's say the pink is the program distribution. And then after that, if you do adjacent bit-line programming, then you may shift all the VTH a little bit larger. This shift is not very large, but you will shift a little bit. So you will shift the VTH by a little bit to the yellow curve. And then after the adjacent word line programming, you will further shift the VTH to the blue curve here. So think about the multi-level cell, or let's say MLC or TLC, you have so many levels here. So that means after programming, the intermediate state here, this, for example, the level A, your threshold voltage distribution may shift up due to the coupling. So as we discussed before, like the TLC only have like hundreds of millivolts margin between the levels. So this kind of cell-to-cell coupling will introduce a lot of errors. So here, especially in the tail will shift up. Therefore, you may create many errors in the flash array. So as we scale, this coupling becomes stronger. That means the shift will become larger. So this is one of the major limitations for us to scale to like 10 nanometer dimensions in the two-dimensional space. So there are some strategies to reduce this coupling effect. So the coupling, if you look at the structure, this is like the cross-sectional view of the a string. So you have floating gate 1 and floating gate 2, and then you have the interpolling dielectric, and then you have the control gate as your word lamp. So floating gate to floating gate, so the coupling is really here through this interpolling dielectric between those two. When you program this one, then part of voltage drop across here. So one way is to reduce the floating gate height. So this is polysilicon. So you can reduce the height. Therefore, here this coupling, this capacitance depends on the overlapping area, right? If you reduce the height, then the coupling capacitance will reduce. And ultimately, you can have a flat. This is called a planar control gate. So here the interpoly. So this high K material only be like flat. So between the floating gates, then you won't have this direct coupling. So this can reduce the coupling ratio. So this can reduce the cell-to-cell coupling. However, this may negatively impact the alpha CG. If you recall, this is the control gate to the floating gate coupling ratio. You also need this capacitance to couple from your control gate to the floating gate. This is how you apply voltage, your wave programming here. You want this wave programming to drop on this one, okay? Not on this one. If this is a selected cell, then you want this one to drop on here. So you still rely on this IPD, this capacitance, to transfer the voltage from the control gate to the floating gate. As you do this planar control gate, then the coverage from the control gate to this floating gate will reduce. So there's a trade-off. So shrinking the height of the floating gate will reduce the coupling between the cells, but also it will reduce the coupling from the control gate to the selected floating gate. And another way to reduce the cell-to-cell coupling, as we discussed before in the DRAM as well. So DRAM, if you recall, we want to reduce the bitline capacitance, right? So we introduce lower K material as the isolation between the bit lines. So similarly, in the NAND flash, what you can do is to introduce lower dielectric between the word lines, and the lowest dielectric constant or permittivity you can get is air, right? So here between the word lines, you can introduce this air gap. So here is the schematic between the word lines. Previously, you may fill this with some dielectric, like silicon nitride or silicon dioxide. But what you want to do is to remove this material through the fabrication process to introduce air between the word lines. Therefore, you can minimize the cell-to-cell coupling. And here is some data to show the improvement of the coupling. So here is the distribution. As if you don't do this, then you may have the tail towards higher threshold voltage. But if you introduce air, then this tail shift can be minimized. So the air gap has been adopted in the sub 20 nanometer generations. I believe this was introduced by Samsung first in the sub 20 nanometer 2D NAND flash. So any questions? So here we discuss the challenges related to the coupling. And the next one is the retention due to the few electron problem. As we discussed, so the number of electrons in the floating gate is less than like 100. So if you lose one electron, you may change significantly of your threshold voltage. So here, this is like retention time in the years and number of electrons. So here, since we only have 200 in the 35 nanometer node, we have 200 electrons, and the retention time reduced to like 3.3 years. So here, for the multi-bit cell, we will have even worse retention time due to the less margin between the levels. So we have to distinguish like 10 electron versus 20 electron versus 30 electron in the floating gate. And also the RTN, the random telegraph noise, may cause the temporal VTH shift. So this is discussed briefly in the logic transistor. If you have trap in the oxide, this can temporarily capture and emit the electrons, so it will cause the temporal fluctuation in the threshold voltage. So then that means the VTH distribution, you need to account for the margin of this temporal variation. That will further reduce the margin between the multi-level cells. As we scale, then the RTN will become more significant. So those are the reliability or scaling challenges related to the 2D NAND flash. So we have many troubles in scaling the 2D NAND flash. That's why we have to switch to the 3D NAND flash, as we discussed in the next. But before that, I'd like to briefly talk about the charge trap transistor. This is a different style of the floating flash transistor, a little bit different from the floating gate. For the two-dimensional NAND flash, mostly we use this floating gate transistor as we discussed so far. But for the 3D NAND flash, the industry mostly switched to this charge trap transistor, or sonus or monos kind of structure. So let's briefly discuss the differences. The principle is very similar as the floating gate transistor we discussed so far. So here, this is the regular MOSFET, and then floating gate, as we discussed, we insert a polysilicon floating gate in the gate stack. And then for the charge trap transistor, the only difference is that here, this floating gate becomes nitride. You still have the oxide between the control gate and this one. The floating gate now become a nitride charge trap layer, and then you still have the ternal oxide down to here. So the whole gate stack becomes ONO. This is like the nitride replace the polysilicon here. This is a key difference. The polysilicon is replaced by the nitride, like silicon nitride. And the Venn diagram of the sonus, this is called sonus because it's silicon and ternal oxide, and then silicon nitride as a charge trapping layer, and then the silicon dioxide as the interpoly. Now it's no longer interpoly, but it's basically the blocking oxide, and then polysilicon in this case as the control gate for the word lamp. So here, the major motivation for this Sonos structure is lower programming voltage, even less than 10 volts, and also it may offer better endurance and data retention compared to the floating gate transistor. So one key difference is that in this kind of charge trapping mechanism, so if there is a loss of the charge, it will be local. So what does this mean? So in the floating gate transistor, as we discussed before, if you have some leakage path here, for example, somehow this part, you may have some leakage path. So electrons in the floating gate, this is polysilicon, is conductive. So the electrons may move around. So if you leak one electron, all the electrons may follow this path. Then your data retention may be poor. But for the silicon nitride, this is more like a semiconductor or like an insulator. So the electrons are locally trapped in the nitride layer. So if you have a leakage path, so the electrons in here will leak out, but other electrons will not move because the silicon nitride is not conductive. So you only have the localized leakage in the patch trapping layer. If you lose one electron, then you lose one electron. You won't lose all of them. So this is another advantage of this patch trapping layer compared to the conductive polysilicon. So the operation principle of the Sonos structure, the charge trapping, is similar as the floating gate transistor. So for the erase, you apply like a negative voltage on the control gate, or you apply positive voltage into the substrate. It's the same thing. And then here the only difference is that in the erase, here the hole may play a role. Because in this band diagram, the hole, like the barrier for the hole, is not that high. Therefore, in this case, the hole, in the erase case, the holes in the substrate, because it's p-type substrate, you have many holes, and holes may inject into the floating gate, not floating gate, I should say the charge trapping layer. So to compensate the electrons, so previously in the floating gate, only electrons go out in the erase. But in the Sonos structure, the holes may also go in. Therefore, the holes can recombine with the electrons. But for the programming, still mostly it relies on the electrons injected into the patch trapping layer. And actually, the nitride-based charge trap transistor has a long history. So here is the evolution of the structure. First, there's no there's no blocking oxide here, so it's purely like a nitride in this part. And then later it becomes this Sonos structure, like a ONO structure. And then in like 2005, it changed to this so-called Thanos structure. So here the blocking oxide changed to like aluminum oxide, and this is becoming the platinum nitride. So it's called Thanos structure. But the 3D NAND flash today typically use this kind of structure. Mono structure. This is metal oxide, nitride oxide, silicon. So it's MONO silicon. So it's called mono structure. And this has become the mainstream technology for today's 3D NAND flash. So any questions? So the charge trapping similar as a floating gate. The major difference is the polysilicon become a charge trapping layer made of the nitride, silicon nitride. Okay, so then let's talk about the 3D NAND flash. As we discussed, the 2D NAND scaling has been slowed down and then eventually stopped around 14 nanometer load. And then at the same time, in like 2013, 14, 15, the 3D NAND flash starts being introduced into the market. And then here the 3D NAND flash, the scaling of that is to increase the number of the 3D layers instead of shrinking the lateral dimension. So the goal here is to make it higher and higher. Previously, the goal is to make the lateral dimension smaller and smaller. So let's review the 3D NAND flash R&D 10 nm. So the 3D NAND flash was first introduced by Toshiba in 2007 in the conference Symposium of VLSI Technology. And this is called Big Structure. This is the first paper reported the 3D NAND flash. And we will review this paper in more details in the next few slides because this is very important as the first work to introduce the 3D NAND flash. And then 2009, at the same conference, Symposium of VLSI, so both Toshiba and Samsung reported their 3D NAND flash. And then after that, other companies also introduced their structure. And then in 2014, Samsung reported their first commercialized product in the ISCC conference 2014. So we will discuss the 3D NAND flash in more details in the next few slides. So if you think about the 3D NAND flash, actually there are many ways to do the 3D stacking. So the first one is this simply stacked NAND flash. This was never used in the industry. This is just a concept. So the idea is very simple. You can just fabricate the two-dimensional NAND flash layer by layer. You can repeat all the process layer by layer. In principle, let's say you have first made your first layer as a 2D flash, and then you make your second layer and third layer. So then in this case, the channel will be horizontal, gate will be horizontal. You just repeat the same process on the vertical dimension. But this will not be good in terms of the cost per bit. And this approach actually was used for the 3D X-point process we will discuss later, like Intel. They have this Optane SSD for the phase change memory. We will discuss that later when we talk about the emerging memories. But this was not used for the NAND flash. So the NAND flash is to use this shared, either shared vertical gate or shared vertical channel to do the 3D stacking. So here the second one, this approach is called the vertical gate approach. So here the thing is that we have to share this gate, which is a green lamps. It's like today's nanosheet transistor actually. So if you recall the logic nanosheet transistor as we discussed, so you have those like nano wire or nanosheets, multiple layers. And then we have to cover, it's like FinFET, right? We have to cover the fin with the Verlan. So in this case, these green ones are these vertical gates covering multiple horizontal channels. So the good thing about this is to share the gate, because we want to share the fabrication process. That is a key for the 3D stacking. And then finally, this one was used in the real product. This is called the vertical channel. This is like the vertical gate-all-around transistor, which we discussed before for the DRAM, the future generations of DRAM access transistor. What you want to do is to build a vertical like nanowire. This is your channel. Now channel is becoming vertical. Previously, those channels are horizontal. Now the channel is vertical, current flowing like vertically. And then you have the wire length gate surrounding the channel, multiple layers. So this is the vertical channel, horizontal gate. And today's NAND flash on the market all use the last approach, this vertical channel. And Samsung call it VLAN, vertical VLAN. So the key is to reduce the cost during the fabrication. We will discuss that in a minute. So the idea is that when you do the 3D stacking, for example, if you do the first approach, you can stack multiple tiers on the same like two-dimensional space. So you save the area, but you may not save the cost. So essentially what we care about, or not, let's say what the industry care about, is the cost dollar per bit or per gigabit. So how much money you spend to fabricate 1 bit of your data storage. So this relies on two things. First is the density of the design. For example, let's say dollar per gigabit. So how much you pay for 1 gigabit? Depending on the density, gigabit per millimeter square. On the, let's say if this is a 1 millimeter square, millimeter by millimeter. So on this 1 millimeter square, how many cells you can pack onto this 1 millimeter by 1 millimeter? So for the 3D stacking here, of course, you can pack more bits on the 1 millimeter by 1 millimeter square. But it may not reduce your cost, because you need to also consider the dollar per millimeter square. This is your density. This is your fab cost. So for the simply stacked NAND flash, the fab cost also increases, because the fab cost is related to how many fabrication steps you introduced in this process. If you do the simply stacking, you need to repeat all the fabrication steps layer by layer. And the most expensive step in the fabrication is the litho. So litho here is the most expensive. If you do the layer by layer, you have to, if you have n layers, you have to repeat n times of the lithography. Therefore, the dollar will increase linearly with the number of layers. So you will not save the dollar. Because if you stack more layers, you need to repeat more fabrication steps. You only save the silicon wafer, the substrate, like substrate cost. But then all the fabrication cost will be added up if you do this simply repeated process. So the idea is to share the lithography across multiple layers. That's the idea behind the second and third approach here. The second approach, what you share is the gate patterning. So for example, you pattern this gate because they are shared across multiple tiers. So you only need to use one lithography to do the gate patterning. And similarly for the vertical channel, you only need to have one critical lithography to define this vertical, this pinner. You want to share the lithography step across multiple tiers. No matter how many tiers you have here, you only want to do one lithography. Therefore, you reduce the cost. So that's the main idea behind the 3D NAND flash. So here, let's have this discussion again. So this is a 3D memory family, and you can have that into two categories. And the first one is the stacking, simply stacking. As we discussed, you simply repeat the same fabrication process as a two-dimensional process. So this will increase your lithography mask count. And then the examples are this cross-point memory, the 3D X-point, we will discuss later, like Intel and Micron introduced. And the simply stacked NAND flash, nobody uses that. And the second one is the vertical type. This is either to share the vertical channel or vertical gate. And then here, if we share the vertical gate, this is the second approach. And this was proposed by Macronix, a Taiwanese company, back in 2010, I believe. So, but this was never put into the production. So the only one that is introduced into the production is here, the blue path. So this vertical channel vertical. And then for the channel vertical, actually there are two possible paths. One is the gate first process, the other one is the gate last process. So here the gate first process still uses a floating gate transistor, and then the gate last process uses a charge trap transistor. So I would say nowadays, so there is a history here, okay. Intel and Micron historically worked together to develop the 3D NAND flash, and then they use this gate first approach. But I think those two get divorced like 2 years ago or 3 years ago. Now Micron joined this approach. Only Intel is working on this gate first process. Now all the major manufacturers, including Micron, like Samsung, SK Hynix, Toshiba, SanDisk, or Western Digital nowadays, I should say, they all use this gate last process. So we will discuss it in a minute. And all the major companies, as we discussed, offer the 3D NAND flash on market today, and you buy them from the market nowadays. So let's look at the first paper from Toshiba. This was the pioneering work to basically have this breakthrough in the 3D NAND flash in 2007 in the symposium on VLSI technology. So this is a paper. I will not go into the details of this page. We will look at that one by one in the next. So here, let's look at the, by the way, this is called the BICS. It's called because it's after the bit cost scalable technology. The reason is bit cost scalable because it shares the lithography step as we discussed earlier. So then it's bit cost scalable. So here, this is the schematic for the 3D structure. And we have many of those vertical yellow pillar. So those are the channels. And then those are the channels, as we discussed before. And then many green lamps, those are the word lamps. And then on top of that, you have the string select. And bottom of that, you have also the ground select. So this is like, so basically it's like one vertical string. You know, NAND flash, you have this string, right? Now you basically stand up this string vertically. And then here we have the word lamps controlled by those word lamp contacts. And in this first paper, the cell size is like 3F by 2F, but if you optimize that, you can get 2F by 2F. but this is the very first work. So the cell size vertical, let's say naturally is like 3/2f. So let's look at the cross-sectional view. You make a better idea what's here, what's in here. So schematic from the circuit point of view, you have this vertical string, right? This is a one-line string. And then you have the floating gate, or not floating gate anymore, let's say the charge trapping layer. So you have the charge trap transistor in series. And then the top one, you have the string select. Then you have the ground select. And then here you see the channel is vertical. And then this pink region here is this charge trap layer. And then you have the wire lamps here. The green ones are the wire lamp. So this is like the cross-sectional view of the big structure. So what is more important for you is this circuit schematic. You need to understand this. So here's from the circuit point of view, this is a net list for the 3D NAND flash. And you will have many strings vertically standing up, and each string is one pinner here. And then the strings are collected here by the bit length. And then the wire length will be multiple layers. One layer is one wire line in this case. And this wire line is shared between those. So here you see those three. So for example here, those three transistors control gates are connected together, right? And then they are shared at the end of the wire line. So those are shared on the same layer. This is the wire line. And the upper string select, sometimes it's called SSL, string select line. And then the string select line, here, pay attention. This is a split. This wire line is shared. So you see the SSL is split. That means you have individual control of each string. Otherwise, you cannot distinguish. You must have the SSL split. So when you select the string, you have to decode the SSL. For example, you select this string. So this string, you apply voltage here, and you ground the other string select. So this pinner is selected. So you read out the data from this string. And the lower ground select line is shared because here this is a ground select line will control one block. So this is shared at the bottom, but on the top here is split, separate. And if you want to correlate back to the 2D NAND flash, what you can do is, if you look at the XYZ plane, XYZ. So here, actually the YZ plane, if you have a YZ slice, is the same as the 2D NAND flash. So if you look at the very outside, this like vertical slice on the YZ plane, this is the same as the 2D NAND flash. You have many of course, you tilted that by 90 degrees, right? So for 2D NAND flash, you have that horizontally on the surface of your silicon, and then now you tilt by 90 degrees, then that will become this YZ plane, and you have many of this YZ plane, like vertically standing up. So that is how you build the 3D NAND flash from the circuit, equivalent circuit point of view. So any questions here? Yes. So the gate, actually they're not physically separated. They're connected together. It's a plane actually. It's a plane. Of course, you may have the slit. There are some like isolation between the wire lamps, but at the end of the wire lamp here on this region, they're collected together. There's like a plane of the metal, so they are shared. And this is the wire lamp contact region. Actually, all the wire lamps here coming out, the metals will be collected together here. And then this region, you make the contact wire to connect to individual wire lamps. So we'll discuss it in a minute. This is called wire lamp staircase region. So let me see if any questions online. So this is the staircase region. So here the key idea is that for the memory array here in the center, we can use one lithography to fabricate this. Because you can deposit multiple tiers and then you dig a hole and then etch this vertical pinner. So you only need to use one lithography to define the pattern or location of the pinner, and then you etch. So you only need one lithography, even though you have many layers. But the wire lamp staircase here, you have to collect two individual wire lamps. You have to collect two individual wire lamps. Therefore, you have to make the staircase, because later you will have like this contact wire land on individual layer to collect to the wire lamp, because here there will be like wire lamps. You need to collect wire lamp 1, 2, 3, 4, 5. So here then the challenge is that we have to use also one lithography to do this step. Otherwise, it will lose the benefit of the 3D stacking. As we discussed before, we don't want to spend as many lithography steps as the number of layers. We want one litho step for all the layers. But here you want to make this staircase pattern, use one litho step. So there is a trick called this photoresist slimming or trimming process. So what you want to do here is, this is a photoresist, and then this is multiple tiers, like your wire lamp contact region wire lamps. So you do the reactive etching to basically etch out this part, and then you have to slimming or trimming the photoresist a little bit. You don't do another litho. So with the existing photoresist, you use some chemicals to make it thinner, to basically shrink this a little bit. Then you do the etching again, so you etch out this part. So you make a stair, and then if you keep shrinking that a little bit every time, then your photoresist will become smaller and smaller, shrinking, and then you can make more and more stairs like this. With only one litho step, you only pattern initially this big photoresist, and after that you keep reusing the photoresist, but you do multiple etching. Because the photoresist, the mask count is the most expensive part of the fab. You want to reduce that. So this is a major trick to do the wire lamp staircase region. So you may imagine this verland staircase region may consume quite significant peripheral area, because this is a memory array, and then you have to make individual contacts to each layer, because the verland needs to come out from the edge of the array. So you have to make this stair like this. And then if you have more layers, you can imagine, right, this horizontal space to make the staircase pattern will be larger. And indeed, this is an overhead for the area of the design. And next, I will briefly talk about this second paper from Toshiba. This is presented in VLSI 2019. 2009. So this is a P-shaped bit cost scalable technology. So the only difference is that then here they make the two adjacent pinner collected by this U shape. I don't know why it's called P shape, but basically you have this collected together. Therefore, your source line can be put on top here. Previously, the source line is on the substrate, but now you can make the source line here with the metal. So that's the only difference in this P-BICS structure. So effectively, in this case, your string will be like folded like this way, because here the two adjacent pinner are connected. And at the same year, Samsung introduced this T-cat structure, and this is a basis for later Samsung's 3D vertical land. But if you look at the structure, it's very similar to the Toshiba's design. And the only difference is that here it uses metal as the verland instead of the polysilicon. And other than that, it's very similar as the Toshiba's design. I will skip the details. So let's have more look. So here I like those schematic, because you can look at the 3D view of the design. And basically here this is a staircase region as we discussed before, and then you have the memory holes or the pinner. So you need to dig a trench and then make this vertical panel region. And then you need to make at the end of the pinner, you need to make these bit lines. So if you look at the pinner here, this is a zoom in. So the pinner actually today will have an oxide core in the middle. And then here in this example, here the green. So the channel is not the center. The channel is like a shell. It's a core shell structure, core shell. So the core is oxide, it's not conductive. The channel is a polysilicon. In this case, is the green part, is a shell surrounding the core. And then you have other surroundings for the charged tungsten oxide. Here, silicon dioxide, the yellow one. And then the nitride, the charge trapping layer, the pink one. And then you have another silicon oxide for the blocking oxide. So your ONO structure will surround that. So from the center to the edge, so if you look at the top view of the pinner, if you zoom in to this pinner, you will see the core is like the silicon dioxide. And then you have this channel region. This is from the top view. You have the poly channel, polysilicon. And then you have the ONO structure. So this layer, I make it simple, okay. So actually this represents 3 layers. It's ONO, the charge trapping layer, tungsten oxide, nitride, blocking oxide. And after that, then you have this metal verland. So it's like a core shell structure from the vertical point of view. It means look at the 10 here. So let me finish this quickly. So this is the process flow for the gate mask fabrication for the trap transistor. What you will do in the fabrication is to deposit multiple tiers of this oxide and nitride, like sandwiched structure first, and then you etch the hole by this one critical lithography step. So you etch the hole, and then you fill in the hole with the polysilicon channel, and then ONO structure at the edge. And then you fill in the middle hole with oxide. And then you etch the slit. You etch through, make the small sub-block. And then you remove this pink part, which is the nitride. And then you refill the metal to the word line. This is gate mask. Gate is a metal gate. You refill the blue metal, and then you etch the metal. So it's a very complicated process in the fabrication, actually, and it's really demanding for the etch process and refill of the material. I will not go into the details of the fab process, but this is a very sophisticated, complex fabrication. And then this is like a gate first process for the Intel's process. I will skip that, and you can look at the a flow here by yourself. But I don't think we will emphasize too much on the fabrication process in this course. This is for your information. All right, so any questions before we stop here? What is the benefit for the core shell structure? So I think you want the channel to be fully depleted in the vertical string. Therefore, you have to use the core to make the channel very thin. Because in the vertical NAND flash, as we discussed, the dimension, the feature size actually is relaxed to be like, for example, the diameter may be 100 nanometer. So if the 100 nanometer is filled with polysilicon, then you cannot make the polysilicon fully depleted. And you need the polysilicon to be fully depleted. Therefore, you have to make this center part to be like a silicon dioxide and make the silicon channel very thin. So your gate, control gate, can fully control the thin channel. If the channel is very thick, it's like a bulk transistor, then your gate cannot control the center of the channel, which is not good. You want a fully depleted channel. That's why you have the core shell structure. All right, so I think that's for today. Thank you.